Welcome back to AP Physics. Today it's time to ponder magnetic fields. So you can see the overall key concepts from this chapter. Today we're going to focus on these first four, looking at what causes magnetic fields, then forces on charges, directions, and motions of particles. So let's consider first of all what causes magnetic fields. We've talked a lot about electric fields. So let's relate it to electric fields. The cause of an electric field, a charge. As long as you have a charged object, it will attract and repel other charged objects. Now, magnetic fields, a little bit different. In order to have a magnetic field, you need a charge, but that charge must be moving. So, any charge causes an electric field. Once you have that charge moving, then it will cause also a magnetic field. So if we consider things that produce magnetic fields, we have regular, ordinary, permanent magnets, and also electric currents, which we'll get into more detail on. If we ponder regular permanent magnets, and really what causes a permanent magnet to be magnetic, you have to go all the way down to the level of the individual atoms. In an atom, if magnetic fields are caused by moving charges, then you need to think in terms of an atom what motions there are of charges. So in terms of motions, protons, well, they're kind of stuck in the nucleus. They can't do a lot, but they can vibrate. And they can also spin. Either or a combination of those two motions can result in a magnetic field. Electrons can also vibrate. Think about when we talked about light being produced last year. Electrons vibrated between electron orbits, producing an electromagnetic wave. So that vibrational motion of an electron between shells can produce a magnetic field. Electrons can also spin to produce a magnetic field. And then, probably the more obvious, the orbital motion itself, that linear motion, circular but still analyzes a linear motion, can cause a magnetic field also. So when you have a substance that is a permanent magnet, basically what you have is motions of the charged particles. Now, if you think about it, every atom has charges. All charges, at least the electrons, are always moving in an atom. So then why are not all substances magnetic? It comes down to balanced motions, basically. If you have an electron, for example, orbiting, we'll say, in a clockwise direction, it will produce a magnetic field. Well, what if you have another electron that's orbiting in a counterclockwise direction? Then it'll produce an opposite magnetic field, and they will negate each other. So a lot of times in substances, what you have is motions that are balanced, and you have no net magnetic field of the atom. Some of these motions you don't have in atoms also, like vibrational motions and spinning motions. Those are characteristics of specific atoms, specific elements, and not all those have those motions. So really then, oftentimes it comes down to the electron orbit. You have a substance that is inherently magnetic if you have an imbalance in that motion, and that doesn't occur for too many substances. The general category of substances that does occur for is called ferromagnetic substances, typically iron-based substances and then some, and we'll get into more details on that. Now, if we think about a magnet, on the most fundamental level, we have an atom here. I'm just going to go a circle with an A in it. And this atom, if there is inherent motion, will produce a magnetic field. So I'm going to draw an arrow over the top of this, indicating that there is inherent motion there and it is producing a magnetic field, and the symbol for a magnetic field is a B. Well, when you have a substance that is permanently magnetic, what you have is a bunch of atoms that have those inherent motions that are producing a magnetic field as little, basically, atom magnets. When you cause those to align, for example, you put those atoms in a strong external magnetic field, you align the little atom magnets, and you cause a substance to become a permanent magnet, as shown in the top figure. Now, in that case, when you break a magnet, if I break right there, I still have atoms, once I draw a few more, on both sides that produce magnetic fields. So then what I have then is, when it's broken, two separate magnets. I don't separate the north and south pole. In fact, each little atom magnet has a north and a south to the magnetic field that it produces. So I just separate the atoms and I end up with two smaller magnets, each with a north and a south pole. If I break it again, same way, I just end up with smaller magnets that have a north and a south pole. You can break essentially all the way down to the level of an individual atom and still have a tiny permanent magnet. Some general things about magnetic fields. Directions, kind of like charges repel, opposite charges attract. North poles, in terms of magnets, will repel each other. South poles will repel each other, or like poles repel. Opposite poles, north and south, attract to each other. For an electric field, we drew field diagrams. And so if I had a positively charged object, then we always denoted the direction of the electric field in the direction of a positive test charge. So from my central object, that positive test charge would be repelled away. An electric field that would look like that. A magnetic field also has a direction. Here are some pictures in terms of what a magnetic field looks like. Instead of using a positive charge, we denote the direction of a magnetic field as the direction a north pole is attracted. So that basically means from north towards south. So then on our magnetic fields here, we're pointing the arrows, the red side of the arrow, towards the south right here. On the lower diagram also, our arrows are all pointed toward the south region. So instead of a positive test charge, it's the direction that a north pole would point, denotes the direction of that field. Now a little more on directions. We will, from here on out, be dealing in 3 dimensions. So in 3 dimensions, we have to be able to easily deal with coming into the page and out of the page. And so these 2 notations basically really come from the idea of an arrow, like a bow and arrow. So there's my arrow. The diagram on the left over here, these X's that are right there denote that you're looking down the back side of the arrow. The feather's on an arrow, and so this would denote a field that is going away from you, or more specifically into the page. So sometimes when we write that field, B being the symbol here, and then an X, sometimes circled, that would denote a field that is going into the page there. On the other side, my dots that we have here, that would be like the tip of the arrow coming at you. And so this would be toward you or out of the page. So if I was denoting a magnetic field coming straight out at, B and a dot next to it, and again sometimes you'll see a circle around that dot. The needle of a compass is basically a small magnet, and that small magnet is balanced so that it can align in Earth's magnetic field. The small magnet that is there, a compass, points north. That end of the magnet would be the north end of the magnet, but magnetic fields are directed in the direction that a north pole is attracted, and a north pole would not be attracted to north, but it would be attracted to south, which means if we consider Earth's magnetic field, the geographical north is not the magnetic north. Your compass over here points towards the geographical north, but the geographical north is actually your magnetic south. So compass needles do point north, and you just have to think in terms of the distinction between a geographical north, which is the north we're used to calling north, and a magnetic north. The magnetic north is actually at Earth's geographical south pole. Now, the Earth has a magnetic field because the molten core of the Earth, you have moving fluids, there are charges, you have moving charges, and so as a result, that produces a magnetic field for the Earth. It is very small. Here are some values for different magnetic fields, and your unit of a magnetic field, and we'll talk more about it, the unit of a magnetic field is a Tesla. A Tesla is a very large magnetic field. As you can see here by Earth's magnetic field, 0.5 times 10 to the negative fourth Teslas. Your average bar magnet, about 10 to the negative second Teslas. If you've had a MRI, which is a magnetic resonance imaging, then you've been in a strong magnetic field. Inside a magnetic field, depending on what they were doing, anywhere from maybe 1 Tesla up to 2 Teslas, and those are extremely strong magnetic fields. So generally when you're dealing with magnetic fields, you're dealing with a value that's going to be less than 1. Now let's consider magnetic forces. Diagrammed here, we have a charge, positive charge, and it's moving at a velocity v into a magnetic field, and by our symbols here, this magnetic field is directed into the page. It will experience a force. Well, let's consider what that force is going to be and what it's going to do to that charge. Here we have a positive charge in the center of the screen. And that positive charge has a velocity indicated by the black arrow up towards the top of the screen. The pink arrows indicate the direction of the magnetic field, which is also going towards the top of the screen. So I want to walk through different things, make some observations in terms of what that magnetic force depends on, and then what it does to the charge of the object. So first of all, I'm going to start with my object at rest. So now I have a positive charge at rest. I'm going to play the simulation. Notice what happens when the charge is at rest. Absolutely nothing. Resting charges do not experience any force due to a magnetic field. And now I'm going to have it moving parallel to the field. It's moving upward, the field is upward. Parallel moving charges experience nothing when they're in a magnetic field. Now we're going to move it perpendicular to the field. So notice we've changed our field direction. The field is now going into the page or into the screen, and we have 3 different objects. If we play the simulation, the object with no charge goes uninterrupted, does not experience a force. The positive and the negative charge, though, do experience forces, but in a little bit different fashion. The forces cause those charges to move in a circular path. If you're going to have a force that causes an object to move in a circular path, you should immediately think in terms of centripetal force, and you should immediately think that that force is directed to the side of the motion, of the velocity. Now I'm going to double the speed compared to the last one, how these charges move differently. Now your charges are still moving in circles, but now they're moving in circles of a larger radius. Now I'm going to change my charges. Looking up here at the top, you've got the 3Q above the charge that's at 6. The 2Q is the charge that is just to the right of 6 units, and then the Q is the charge that is over at the 8. If I play, they all have the same velocity. The 3Q is experiencing the most force, causing it to go in the tightest circular path. Correspondingly, when we move out to the outer one, the charge of Q, it's experiencing the least force, causing it to go in the largest circular path. So the force depends on the amount of charge that is there. And we go to velocities, V, 2V, and 3V. Now these move in sync with each other, but they are experiencing different forces. They're experiencing different forces, causing them to go in different radii, circular paths. So then the magnetic force also depends on the velocity. So now, if we come back to here, this magnetic force, the magnetic force depends, as we just observed, on the amount of charge. It also depends on the velocity of the charge. It will also depend on the magnetic field. If we had a stronger or a weaker magnetic field, then we would correspondingly have more or less force. So then the force Q, V, and B, for the charge shown in the diagram on the right side, what we observed was this charge in the simulation went around in a curved path. And so then I'm going to go ahead and spell out an equation to calculate the magnetic force, F sub B, that's going to be equal to Q times V crossed into B. So the charge is there, the velocity is there, the magnetic field strength is there also. Now, let's talk in terms of the cross product. Thinking about V cross B, the purpose of a cross product, this would be a QVB sine theta, where theta is the angle between V and B. The purpose of that sign in there, think about torque, R cross F. The purpose of that sign being in there was to put those two vectors perpendicular. Likewise, this cross product is there to make these vectors perpendicular to each other. To apply the cross product, so on the right-hand rule, fingers in the direction of V, then you wrap to the direction of B, then your thumb gives the direction of the force. I'll show this live here in just a minute. So then applying this back to our diagram here, our charge V is entering the magnetic field. And so when it does, if I point my fingers of my right hand in the direction of the right, and I wrap them into the direction of the field, which goes straight down into the screen, then my thumb is going to point a magnetic force that is straight upward. If I continue the motion of the charge a little further, say to up here, then my velocity will be tangent to the path. And so if I point my fingers diagonally upward towards the top right-ish corner of the screen, and then I wrap them so my fingers are pointing straight down into the screen, then my thumb is going to point diagonally upward in this direction. And so then what you have is that magnetic force is always changing directions, and it's always going to be pointed towards a central point, and so it will act as a centripetal force. Another way to think of this, QV cross B. V cross B, again, we talked about the purpose of the cross product, making those two vectors perpendicular, and then your thumb is perpendicular to that. Well, that means that V and B really define a geometric plane, and then the magnetic force will be perpendicular to that plane that is defined by V and B. So then once you know the directions of V and B, picture what is perpendicular, and you got two choices. So V and B define the horizontal plane. Force is either going to be vertically upward out of the plane or vertically downward out of the plane. All three vectors are mutually perpendicular once you apply that cross product. So now let's consider an example. So we have a proton that's traveling 2 times 10 to the 5th meters per second east in Earth's magnetic field, and you're given a value for the magnetic field. So then V is equal to 2 times 10 to the 5th meters per second. B is equal to 0.5 times 10 to the negative 4th Teslas. And we want to calculate the magnetic field or magnetic force acting on the proton if it's in Cincinnati, where Earth's magnetic field is directed due north. Okay, so we know it's a proton. So in part A, F is equal to QV cross B. Our magnetic field is directed north. Our velocity is to the east. Those are perpendicular to each other. And so then F sub B, our Q, 1.6 times 10 to the negative 19th coulombs. Our velocity, 2 times 10 to the 5th meters per second. The magnetic field, 0.5 times 10 to the negative 4th Teslas. And then times sine of 90 degrees. Okay, that's going to give us a value of 1.6 times 10 to the negative 18th newtons. Now, in terms of the direction that that force is going to be acting, this direction is north. Okay, and so into the page, into the board is north. Okay, from there, this direction would be east. This direction is west. Coming out of the board is south. Okay, right hand rule. QV cross B. So my velocity is to the east. So I'm going to point my fingers towards the east. My field is towards the north. So then what I'm going to do is I'm going to rotate my wrist so that then I can wrap my fingers into the board in the direction of B. My thumb points upward, and upward is the direction, upward is the direction of the force. Just a side note, remember, north is not upward. North is a direction on the surface of the Earth. Okay, so then our force acting on the proton in Cincinnati is 1.6 times 10 to the negative 18th newtons in that upward direction. Part B, we want to calculate what the force is acting if we're in Seattle. Well, in Seattle, QV cross B, your magnetic field is not due north. It's shifted over because you're significantly further to the west. So your magnetic field is directed 20 degrees east of north. Okay. Changing my sign convention just for a second. If I let that be north, then 20 degrees east of north would be right there. And so my magnetic field is here. My velocity over in the east direction, so my cross product angle, the direct angle between V and B, would be 70 degrees. So then when I plug into here, F sub B equals Q, charge of a proton, 1.6 times 10 to the negative 19 coulombs. My velocity, 2 times 10 to the 5th meters per second. B, 0.5 times 10 to the negative 4th Teslas. And then sine of 70 degrees. And so that's going to give me a value of 1.5 times 10 to the negative 18th newtons. Okay, in terms of a direction, now going back from our land directions here, my velocity is still east. I still point my fingers in that east direction. Now I need to rotate to that direction of B, okay? So going towards north, 70 degrees, my thumb still points upward. Okay, 1.5 times 10 to the negative 18th newtons upward. So then thinking about an upward force acting, use your imagination. I don't have a tennis ball. Here's my proton. If my proton is headed east and it experiences an upward force, it's going to go like that and it's going to curve, okay, and it's going to come around and it's going to do a circle like this, okay? Your force is a little bit less in Seattle, and so then you're going to have a larger circle in Seattle than you would in Cincinnati with a stronger centripetal force. Now let's consider a little bit different perspective on those right-hand rules on the problem. For Cincinnati, blue dot down here, our velocity of the particle was to the east. The magnetic field was due north. So then QV cross B, when V crosses into B, when I physically wrap my fingers from the direction of V up to the direction of B with my right hand, my thumb is going to point out of the board, out of the screen, straight at us. When we're over in Seattle, now the magnetic field is not pointed straight north, but rather 20 degrees east of there. And so my magnetic field would be here. My velocity is still to the east. Now when we wrap, fingers in the point direction of V, wrapped into B, I rotate my fingers in that direction. My thumb is still going to point in the same upward direction. So what that angle does, the 70 degrees right here between the two, is it actually reduces the value of that force by a little bit. So then in animation, that's what happens when your velocity and field are perpendicular, and as they go into alignment, when they're in the same direction, V and B, you have no force. When they're perpendicular, you have maximum force, and at any angle between, you're scaling the amount of force based on the value of that sine angle. Now, let's consider a little bit more practice on that right-hand rule. I want you to take a look at these different situations, pause the video, and predict what the direction of the force is. Note that F equals QV cross B gives you the direction of the force for a positive charge. So when you have a negative charge, do the right-hand rule for a positive, and then flip your thumb over 180 degrees. So now let's consider the directions of these different forces. So up here on our first diagram, I numbered the particles just to make it easier. So we have particle number 1, okay, our base equation. Again, that's dictating all of our directions. F equals QV cross B, okay? So then coming over here to this one, V is in that direction. I'm going to wrap my fingers until they point in the direction of B. B is coming out of the board, so I wrap like this. That means my force is going to be downward. And so this particle will come and it will curve in a circular motion in that kind of downward direction. I'm drawing it kind of small so I don't run into the other particles. Okay, particle number 2, there's V. rotate your wrist until you can wrap in the direction of B coming out of the screen, okay? And then the force is going to be in this direction. If the force is in this direction, this particle is going to move over that way, okay? It's going to circulate off to the right. Okay, particle number 3, right-hand rule, QV cross B. Now I need to come downward, rotating my wrist around so that I can rotate my fingers outward. I'm pointing this way. If I'm pointing this way, this particle is going to curve around in that direction, except it's negative. So let me take that direction back off. Okay, we did QV wrapped into B, and we got this way for a positive charge. Flip 180 degrees for a negative charge. It's actually going to go that way. Whenever you have a negative, you have to flip it 180 degrees, okay? Particle number 4, here's V. Rotate so I can wrap my fingers in the direction of B, and so my force is going to be up this way, and so this particle is going to curve around in that direction, okay? Over here, I have 3 different particles. Particle number 1, here's V. B is directed over in this direction, so then I can go V wrapped into B. My thumb points into the board, and so this force, I'm not going to try to draw circulation, that force is into, okay? Particle number 2, V cross B, they're in the same direction. This particle is going to experience 0 force because B and the velocity are in the same direction. Up here, negative particle. So we go V, I'm going to rotate this way, so I can go V wrapped into B. My thumb is pointed outward for a positive, so it'll go into the screen for a negative, and this one will experience a force into the board, okay? Coming down here. Now, my field is diagonally upward, and my velocity is in, so I'm going to point my fingers in the direction of the velocity, rotate around, okay, until I can go from this velocity wrapping in that direction for the field, and my thumb points the direction of the force. And so my magnetic force would be in this direction. Negative ion moves south. Now we know the direction of the force, okay, and we want the direction of the field. So F equals QV cross B. We know our particle is moving south. Where I am standing, okay, north is into the board, south is towards you, and then I have east and I have west. So if my ion is moving to the south, then V, I would point towards you, crossed into B, I want to end up with an upward force. So then what I'm going to do is I'm going to rotate my hand. I want the upward force, and so my thumb is pointed upward, so then I would wrap my fingers in the direction of the magnetic field, which would be in the east direction, but it's a negative ion. So once I do this, I need to flip it 180 degrees over, and so my magnetic field would be in a direction to the west. So let's consider another example. We have the positive charged particle, the proton, entering the magnetic field traveling 3.2 times 10 to the 5th meters per second, as shown in a direction over to the left. On A, we're describing the path of the charged particle. Well, as this particle moves into the field, F equals QV cross B. We would point our fingers of our right hand to the left, wrap our fingers then into the screen or downward, okay, from my point of view. And so what we're going to get on our object is a force in this direction. And so then what's going to happen to the positively charged particle is that it is going to move in this direction, and it's going to circulate. And that's what we're going to calculate in B, C, and D. Now, the first thing we want to calculate is the radius of the path. So it's going to travel in a circular path. Okay, so then when we set up Newton's second law, net force equals mass times acceleration, that force it is experiencing is going to be the magnetic force, QV cross B. We recognize it's a center-directed force, so that A is going to be an A sub C, which means we're going to plug in a V squared over R. Now it's a matter of doing algebra. We already know, based on what was given, okay, that we're at a right angle, so it's going to be the sine of 90. So then QVB sine 90, one of my V's will divide out. And then if I'm solving down for the radius, I'm going to bring the radius up. Okay, I'm going to have an MV left on the right side, and then a QB will divide over to the denominator. So then plugging values in here, this is a proton, so you have from your constant sheet the mass, 1.67 times 10 to the negative 27th kilograms. The velocity was given by 3.2 times 10 to the 5th meters per second over Q, charge of a proton 1.6 times 10 to the negative 19th coulombs, and then the field 0.03 Teslas. That's going to give us a radius value of 8.98 meters. Now, in part C, we want to know the angular velocity. Okay, well, we already know what the linear velocity is. 3.2 times 10 to the 5th meters per second. Okay, I'm going to write this so we can think of it in terms of a picket fence. So this is meters over seconds. We're in meters, we want to be in radians. 1 radian is a radius length. That's a 8.98 meters. So you're basically dividing by the radius. You can also think of that in terms of the equation V equals R omega. You end up doing the same math. So then our angular velocity, 3.56 times 10 to the 4th radians per second. In part D, we want the period. And basically what I'm trying to illustrate here is you can find various different things once you know what the charge is doing in terms of velocity in a given field. So then another thing we can calculate is the period. If we think of knowing either the velocity as delta x over delta t, or omega as delta theta over delta t. Either one, or you could even use a picket fence, okay? I'm going to use omega equals delta theta over delta t. We know our value, 3.56 times 10 to the 4th radians per second. In a period, capital T, it's going to go around once. And once around in radians is 2 pi radians. So then do the math to solve down for the period. 1.76 times 10 to the negative 4th seconds. So kind of in summary, on magnetic fields, they're caused by charges that are moving. Okay? When you have an external magnetic field and you place a charge in that external magnetic field, that moving charge will also experience a force, and that force is going to be mutually perpendicular to both the field and the velocity, F equals QV cross B, which is going to cause the charge to circulate. Okay, so it's not going to speed it up, it's not going to slow it down, which makes magnetic fields very different from electric fields. Electric fields, you always speed things up or slow them down. Gravitational fields, you speed things up and slow things down. Magnetic fields push charged objects to the side and cause them to circulate, and so a uniform magnetic field cannot speed up an object or slow down that charged object.
Ponder Physics.